So let's suppose that a proton particle is traveling along one dimension, let's say along the x-axis, and it has an initial velocity given by VA equals 4 times 10 to the 4 meters per second. Now, this proton collides elastically with the following stationary helium atom. So our helium atom's velocity, VB, is 0 meters per second before our collision takes place. Now, after our collision takes place, our velocity of the proton, VA prime, and the velocity of our helium atom, VB prime, is unknown. And we want to calculate what the quantity, what the magnitude and direction of these velocities are after our elastic collision takes place. Now we know what the mass of the helium and the proton is. The mass of the proton is 1.01 unified atomic mass units, and the mass of the helium is 4.00 unified atomic mass units. Now, we are given the fact that our collision is elastic, and that means we have the conservation of momentum and the conservation of kinetic energy. Now, in a previous lecture on elastic collisions, we derived the following equation using equations 2 and equations 1. So we get that the relative velocity of our two objects before the collision is equal to negative of the relative velocities of the two objects after our collision takes place. Now, if you're uncertain where this equation comes from, go back and watch the lecture on elastic collisions. So we have this equation, and notice that VB is 0. So this term goes to 0, and we're left with VA is equal to negative VA prime plus VB prime. So let's rearrange our equation for VA prime. We get VA prime is equal to VB prime minus VA. So let's label this equation as equation 3. We're going to use it in just a moment. Now, let's take 1 and let's notice that we have MB times VB. And since VB is 0, since our helium atom is 0, has initial velocity of 0, this term goes to 0. And so we're left with the following result. So MAVA is equal to MAVA prime plus MBVB prime. Let's label this equation as equation number 4. Now we take, because we have two equations and we have two unknowns, we can solve for one of the unknowns. So let's suppose we want to solve for VB prime. So that means we can take this VA prime, because it's equal to VB prime minus VA, we can plug this term, we can plug equation 3 into equation 4. We plug this into VA prime, and we get the following result. So MAVA is equal to MA multiplied by this whole quantity, VB prime minus VA plus MB times VB prime. So now we multiply our MAs out and we bring all the terms, all the non-VB prime terms to the right side, and we bring the VB prime term to the left side. We get the following result. VB prime is equal to 2 times MA times VA divided by the sum of their masses. So now notice we have all the values on the right that we do know, and we have the left value, VB prime, that we are looking for. So we can solve for VB prime by simply plugging in our knowns. So 2 times 1.01 unified atomic mass units times the initial velocity of the proton, 4.0 times 10 to the 4 meters per second, divided by the sum of their masses, so 5.01 unified atomic mass units. The mass symbols cancel, and we're left with the following result. So, our VB prime, the velocity, the magnitude of the velocity of the helium atom after our collision takes place, is 1.61 times 10 to the 4 meters per second. And it's positive, which means our helium atom moves in the positive direction along the x-axis. So now we know what one of the quantities is, one of the velocities of the objects after our collision takes place. So that means we can use equation 3 to solve for the final unknown. So equation 3 tells us that our velocity of object A after our collision takes place, our velocity of the proton after collision takes place, is equal to the velocity of the helium after our collision takes place minus the initial velocity of the proton. So we found what VB prime is. It's this value. So 1.61 times 10 to the 4 meters per second minus 4.0 times 10 to the 4 meters per second, and we get negative 2.39 times 10 to the 4 meters per second. Now notice the magnitude is 2.39 times 10 to the 4 meters per second, and direction is negative, which means the proton moves in the negative direction along the x-axis after our two objects collide elastically. So once again, initially the helium atom is stationary and the proton is moving in the positive direction. After our collision takes place, the proton reverses directions and the magnitude decreases because some of that kinetic energy went into the helium atom. And so now the helium atom is moving with the velocity equal to 1.61 times 10 to the 4 meters per second, and it's moving in the opposite direction.